Hello all of you. Welcome to the 51st lecture on the course on analysis and modeling in chemical engineering. In this week, we will discuss about something known as mesh equations that basically provides a framework to solve like problems on separation processes, particularly on cascades. We will first discuss how we develop these equations, and then we will discuss what are the methods or algorithms we can use to solve these equations. So, I will take general framework of separation processes. It can be a vapor liquid stage, which we mostly discuss, but then whatever we are discussing for a general equilibrium stage can be tailored for different kinds of separation processes. For example, if we have a distillation column that also involves a VLE, a vapor liquid equilibrium, and if we have, let us say, an absorber or stripper that also involves vapor liquid equilibrium. The only fundamental difference between the two is in the distillation we require the need for an energy separating agent, basically heat, to vaporize the liquid, and in the case of absorber or stripper, either the vapor or the liquid is a mass separating agent. For the case of absorber, the liquid is the MSA, and for the case of stripper, the vapor is the MSA. With some small changes, whatever we will develop can also be adapted to, for example, liquid-liquid extraction. What will change there is instead of like a vapor and a liquid in equilibrium, we are going to have two liquids in equilibrium, right? So, just keep in mind that the framework itself is quite general, and we can think about other possible choices of the phases. And whatever we are doing now, we will discuss some specific cases for distillation and so on, but in general the framework is quite general and can be adapted to any kind of separation process. But the fundamental assumption is that we are assuming that every stage is in equilibrium, right. In the later part of this week, we will discuss some rate based methods, which are basically looking at the non-equilibrium aspects of it when the equilibrium is not quite attained in every stage. That is, I would say, a more general or more realistic situation, but at least what we have done in the previous week, except the last problem we did in the previous class, we have focused only on the equilibrium based systems, and the same thing will follow for the most part of this week, except towards the end when we discuss about the rate based methods. So, we have in general equilibrium stage J, and what I am showing here is a most general possible situation. All the streams that is being shown here, they need not be present for every particular case, but this is the most general situation that is possible. So, I am assuming that there is a feed coming to every stage. Naturally, in a cascade, every stage may or may not be getting a feed, right, but I am taking in general a feed for every stage. In case that there is no feed, we can always set the feed for the particular stage to be 0. So, there is a feed coming there, and then there is a liquid that is flowing down and a vapor that is flowing up, and liquid therefore comes from the stage above it to the stage below. So, whatever comes from the stage J minus 1 liquid, that comes to stage J, and what leaves is basically what is leaving from the stage J. The Lj is the flow rate of liquid leaving the stage J. Vapor on the other hand is going up, and vapor from the stage J plus 1 enters the stage J, and then what is going out is the flow rate Vj of the vapor. But in addition to this main stream flows, there is also a possibility for side streams which are taken out from the system, and of course, it did not be always the situation, but we are keeping a more general case. So, in case that there are no side streams, you can set it equal to 0. So, we have a liquid side stream that is leaving from the liquid part Lj. So, total flow rate therefore, that leaves stage J, the liquid flow rate is Lj plus Uj. And similarly, for the vapor, we have taken a vapor side stream, that is Vj plus Wj is the total flow rate that is going out there. Naturally, there can also be a side stream for the J minus 1, Lj minus 1 and the Vj plus 1 here, but I am not showing it because I am going to consider those side streams. For example, for Lj minus 1, there is going to be a Uj minus 1, but I am going to consider that side stream when we do the balance for stage J minus 1, right. So, I am not showing it in the balance for stage J. So, for Lj minus 1, the corresponding side stream is Uj minus 1, that we can consider when we do the material balance for the stage J minus 1. Similarly, here also we can have a Wj plus 1, but we do not consider it for the stage J. The side stream Wj plus 1 will be considered when we do the balance for the stage J plus 1. So, in addition to this, we can define the variables, the mole fractions of all the components. So, we have I represents the component. So, I goes from 1 to C, and J represents the stage, and J goes from 1 to N. In every stage, we can also remove some heat. So, Qj is the heat removed from the stage. So, it is going to be plus when it is taken away from the stage, and it is going to be minus if it is added to the stage, right. So, the way we have defined this is going out is considered positive. Then we can assign enthalpy to every stream, and the language that we have used is quite intuitive. So, HF is for the feed, HV is for the vapor stream, and HL for the liquid stream, and we have added subscript, let us say J minus 1, J plus 1 and J corresponding to the stream that it corresponds to, right. In addition, we can define the temperature and pressure for every stream, right. And since the vapor and liquid are in equilibrium, so therefore, I do not differentiate between the liquid temperature and vapor temperature. So, for stage J, the temperature is, let us say, Tj and pressure is Pj, and the same temperature is for the both liquid stream and for the vapor stream, right. There are few more things in the flow sheet here. For example, I am showing a valve because we can involve a pressure reduction of the feed or increase, and also I have added a liquid head that may correspond to a pressure increase, that can be because of the barometric head or whatever. So, we are also keeping a provision for change in the pressure coming down or when the feed is entering, right. That is a more general situation, although those are not being quite considered separately in whatever we discuss. So, what kind of equations we can write for this? Essentially, there are 4 types of equation we can write for this. We can write the material balance, which I will refer as M equations. We can write the phase equilibria, which I will refer as the E equations. We can write the summation of mole fraction equation. So, in every stage, the mole fractions of all the components should sum to 1, both in liquid and vapor. So, those are my S equations. And then there is energy balance, which I refer as H instead of E, because E I am referring to the phase equilibria, right. So, I am using the letter H to represent the energy balance. Okay. So, let us first try to write the material balance for a particular equilibrium stage, and I will call that equation or label that equation as something like Mij, that is for species I. So, I refers to component and J refers to the stage. So, for species I want to write a material balance, and what is it going to be? So, we have to see what is coming in and what is going out. So, we have a feed Fj, the total flow rate is Fj, and the mole fraction, this is the overall mole fraction Z, because the feed can be liquid or vapor or a combination of both. So, Fj Zij is the amount of component I, or the molar flow rate of component I that is coming from the feed. Then the other stream that is also entering is from the vapor that is below it. So, Vj plus 1 stream is also coming. So, we write Vj plus 1 and then the corresponding mole fraction Yi j plus 1. So these are entering, and of course a liquid also enters from the top, so that has to be Lj minus 1 and the corresponding mole fraction is Xi j minus 1. We use the notation X for the mole fractions in the liquid phase, Y for the mole fraction in the vapor phase, and Z for the feed, because the feed can be a combination of liquid or vapor or liquid or vapor. Okay. Then we should look at what is going out. So what is going out is these two streams, Lj and Uj, and clearly they are going to have the same mole fraction. So basically the liquid side stream is being purged from the liquid that is flowing down from the stage J, and so therefore we have Lj plus Uj Xij, and similarly we have Vj plus Wj Yij, that is going out. So this becomes the mole balance, and we are going to have this equation for every component in every stage. So basically we have C equations for each of the stages. Again I remind you that I am not considering the side stream here and here, because they will be considered in the balances for stage J plus 1 and J minus 1 respectively. Okay. Now we can also write the phase equilibria relations for this particular case. What are we going to get? So we have, I can label again the equation as something like Eij. So for component I in stage J, the mole fraction of species I in the vapor phase will be, as we have discussed, some k value Kij for the component in that stage multiplied by Xij. This has to be a minus sign just to make it equal to 0. This equal to 0, right? And again, k is the ratio of the liquid phase and vapor phase partial fugacity coefficient. So k has to come from thermodynamics or the equation of states. So, but for the time being, for simplicity, we are simply writing it as k, but keep in mind that it has to come from some thermodynamic relation or equation of state. Okay. So then we have again C equations for every stage. In addition, we can write the equation for the summation of the mole fraction, and these equations I can write for both the vapor phase present in the stage J and the liquid phase present in the stage J. So here we are assuming that there is no entrainment or occlusion or any kind of intermixing between the vapor and liquid phase. The vapor and liquid are separate phases. So therefore, we can separately consider their mole fractions, right? If there is an occlusion or entrainment, in that case, that situation gets more complicated, right? Okay. So I can write the mole fraction for the liquid. I can label that equation something like Sxj, that will refer to the summation of mole fraction of all the components in the liquid phase in stage J. That should also be equal to 1. And the same thing I can write for the vapor phase, that is again I equal to 1 to C, Yij minus 1 is equal to 0, right? Now, in principle, we can consider both these equations, but just to make our life easy for whatever we do later, I am going to consider only one from these two equations. Let's say I consider only first, right? What do I do with the second one? Instead of this, what I do is I write the total material balance, right, for the system, and I will show what exactly is the material balance we are writing. So we are going to replace one of these equations with the total material balance, right? Otherwise, we cannot consider total material balance separately, because if I add up all the material balances right here, if I just add it up, what we are going to have is something like summation over I equal to 1 to C Fj Zij, and then similarly I am going to have plus Vj plus 1 summation over I equal to 1 to C Yi j plus 1 and so on. And if I take the summation equations as given, in that case what we are going to get is basically the total material balance becomes meaningless, right. But if I do not consider one of the summation equation as in our list of equations, then in that case we can define a total material balance that becomes a separate independent equation in place of the summation of mole fraction equation, right. So, we will take one from here and the other one I will write a total material balance, and that balance I am going to write from stage 1 to stage j, right. So, I want to write that equation from stage 1 to stage j. So, therefore, we are going to have one such equation for every value of j. Every value of j we are getting one equation, that is the balance from stage 1 until that particular stage, right. So, what is it going to be? So, again we can see, so we have an Lj that is coming out from here. So, Lj is coming out from the liquid phase here, and what is that? Lj is basically equal to, Lj should be equal to what is coming in the stage. So, what all are coming in? So, we have all these feeds coming in F1 to Fj, and what is going out are the side streams U1 to Uj and W2 to Wj. In fact, we also have a W1 that I set it to 0, assume that there is no side stream at top, and similarly we also have something like a Un that we also set it to 0. So, there is no side stream from what is leaving the last stage, because what is leaving the last stage anyway is the final product. So, we are not separating anything from there, right. So, with these assumptions, what I can say is this Lj will be a summation over m going from 1 to j. So, I am having Fm. So, basically I am adding F1, F2 to Fj. So, Fm, and we have to subtract what is going out, that is my Um and Wm. So, this is also mean a summation over U's I am subtracting and summation over W's I am subtracting. In addition to that, we have a vapor feed coming in, that is plus Vj plus 1 from stage j, and a vapor going out, that is V1, right. So, therefore, I can get the liquid flow rate leaving stage j in terms of the other flow rates given in the problem, right, and that becomes the expression of the total material balance which I am going to use in place of the summation of mole fraction equation. Okay. We can also write the energy balance for this stage, and the energy balance I will represent as something like Hj for stage j, and there is going to be only one equation for every stage, right, and that is going to be the energy coming with the feed, that is Fj into corresponding enthalpy, then energy that is coming in the vapor, that is Vj plus 1 with the corresponding enthalpy, and energy coming in the liquid, that is Lj minus 1 and the corresponding enthalpy. And then what is leaving is this liquid main stream and side stream. So, it is minus Lj plus Uj into the corresponding enthalpy. All the enthalpies are per unit mole, minus similarly for the vapor leaving, that is Vj plus Wj. By the way, this is not applying here, that was for the summation of mole fraction equation. This is going to be Hbj, right. And in addition to that, there is also a heat that is being removed from the stage. So, we also have minus Qj is equal to 0. So in addition to that, we also are going to have property relations. So we have all this kij's. What do the kij's depend on? They can be considered a function of the temperature of the stage, the pressure of the stage, and the composition of the stage, which is my xi and yi values, whatever we are having for the particular stage, right? Similarly, I also have a liquid enthalpy that is also going to be a function of these variables, and we are also having, in fact, it is going to be a function of Tj, Pj, and only the Xij more specifically, not the liquid. And then we have not the vapor, and Hvj is similarly a function of Tj, Pj, and the composition of vapor, that is Yij, right? And we take that as given, so we don't count them, these equations. We say that it is already given, so it is not being considered separately in our counting. So let us count the number of equations that we can write. So we can write how many m equations? So for every stage, I can write the component balance for all the C components, and then we can do that for all the n stages. So in total, we have C equations for every stage, right? So for how many E equations we have? We have C equations for every stage, for every component. How many S equations we have? We have in principle one, two, but one of them we are basically considering there, and instead of the other one, I am considering the total material balance, right? So basically, I add a plus one in M, and I add only a one here. The other possibility would have been that I keep it C, and I make it 2, but I am only considering one of the summation equation, and instead of the other one, I am writing the total material balance, right? So in both these cases, the total equations should not be changed. Whatever we do, it should not change my degree of freedom, right? How many H equations we are going to have? We have only one energy balance for every stage. So in total, we have 2C plus 3 equations. So in total, for n stages, we are going to have n into 2C plus 3 equations, right? How many variables we can keep unknown? That should also be my n into 2C plus 3. Out of this, I have xij unknowns, which are for n stages C components. So we have nc here. We have yij unknowns, again for n stages C components, nc here. How many ljs? The liquid flow rates going from L1 to Ln, we have n here. Keep in mind that L naught is also 0. There is no liquid coming from the top, right? And there is no vapor coming from stage n. So my V naught is also considered 0 here. So Vj is going from V1 to Vn, that is also n, and temperatures I can define for every stage, that is also n, right? In case this L naught and V naught is present, we can account for that, right? But in the example that I am showing, this counter current cascade, the L naught and V naught is 0, and I have also taken 0 the side streams earlier, Un and W1. Okay. All right. So let us take one example to demonstrate what exactly we are doing. So how we can write a mesh equation, right? So I will go back to the distillation columns, or the train of a sequence of distillation columns that we have discussed earlier. Let us say I want to write the mesh equation for this case, right? And once I tell you this, you can try the second one yourself, right? So what is it going to look like, right? So my feed is going to contain how many components? So we have one component here, C3, second component is here, third component is here, and then we have 4 and 5 components here. And then we have 3 columns, let me call it 1, 2, 3, and I can define the molar flow rate of feed, and I can define the Zi of the feed, where we basically have 5 values of that, right? And we can also define some enthalpy HF of feed, and I can also define some temperature and some pressure for the feed, right? For the first column, I can define the liquid leaving at as something like L1, vapor leaving as V1. From the second column, I can define liquid leaving as L2, vapor leaving as V2. The third column, I can define L3 and V3. So let us write, for example, the M equation for this case, right? So for stage 1, for every component, I can write the material balance equation, and that is going to be something like FZI, that is coming in, and then what is going out is my V1 YI, and what is also going out is my L1 XI, right? And this I can do it for I equal to 1 to 5, right? This is for first stage. Similarly, for second stage, the feed becomes L1. So we have L1 XI, that is my feed, that is equal to V2. This is YI1, by the way. This is the XI1. So V2 YI2 minus, and this is also 1, minus L2 XI2 is equal to 0. And similarly, for stage 3, I am going to have L2 XI2 minus V3 YI3 minus L3 XI3, right? What are the E equations we have? The E equations we have are essentially my Yij is equal to Kij Xij, where I is equal to 1 to 5 and j is equal to 1 to 3. And what is the S equation we are having? Let's say I define both Sx and Sy as the equation in this case. So we are going to have summation over I equal to 1 to 5 Xij is equal to 1 for j equal to 1 to 3, and then similarly I equal to 1 to 5 Yij is equal to 1 again for j equal to 1 to 3. And finally, we can write the H equation for the cascade. Let us write on the next slide. So the H equation is going to have, we have F HF, that is coming in the first stage, and what is leaving is my L1 HL1, and what also leaving is my V1. So V1 HV1, and there is no heat information provided. So you can assume that it is probably adiabatic. So that quantity is going to be equal to 0. Then similarly for stage 2, we can write L1 HL1 minus L2 HL2 minus V2 HV2 is equal to 0. And then for stage 3, I can write, so L2 comes here, this is my V2, this is my L3, this is my V3. So we have L2 HL2 minus L3 HL3 minus V3 HV3 is equal to 0. So in this way we can basically formulate the mesh equations for the stage, MESH equation, and they pretty much becomes the equations that we have to solve, right? Again, keep in mind the property relations we are assuming to be given, so I didn't write it separately, but of course that equation has to be also included in our scheme of things. So with that, I conclude here. You can try doing a similar example here. Here also you can call this as column 1, column 2, column 3, but now the vapor of 1 becomes the feed to this. So I will call this some V2 and some L2, and the liquid of this becomes the feed to is column 3. So I can call it some L3 and V3, and you can try doing the mesh equation for this case in a similar fashion that we have done for the other sequence. So with that, I stop here. Thank you so much.